Take a simple piece of cardboard, cut two narrow slits into it and shine a light through them. It is an experiment so simple that high school students perform it during routine lab hours. Our basic intuition suggests the universe follows a fixed, predictable path. If you fire a physical object at a wall with two openings, it travels through one or the other. It exists in a specific place whether we are watching it or not. In 1801, Thomas Young used this setup to demonstrate that light travels as a wave. As the light passed through the slits, it fanned out and overlapped, creating a pattern of alternating bright and dark bands on the wall behind it, a result that only occurs when waves interfere with one another. For the next 100 years, this settled the debate. The physical world appeared to be a solid, mechanical system where every effect had a clear and measurable cause. That certainty ended in 1905 when Albert Einstein published his work on the photoelectric effect. He demonstrated that light hits metal not as a continuous wave, but as individual, distinct packets of energy called photons. This introduced a direct contradiction. When passing through slits, light acted as a wave. When interacting with matter, it acted as a rigid particle. To understand how light could exhibit two opposing natures, scientists pushed the double-slit experiment toward a microscopic scale. They were looking for a way to reconcile these two models, but instead they found a paradox that classical physics could not resolve. Using 20th century technology, researchers updated the experiment to fire single units of matter, first photons, then electrons, one at a time, toward the two slits. Logic dictates that a single particle of matter must pass through one slit or the other, eventually forming two simple clusters on the back wall. At first, the screen shows exactly that, a single white dot per particle. But over hours, individual dots build an interference pattern. Even fired one by one, particles land as if interfering with themselves, traveling through both slits simultaneously. Einstein refused to accept this result, arguing that the particles must have hidden variables, internal properties that determine their path, which we simply hadn't learned to measure yet. Niels Bohr disagreed, proposing the Copenhagen interpretation. He argued that before a measurement is made, a particle does not have a fixed position. It exists as a sea of probability, occupying all possible paths at once. By the 1927 Solvay conference, the world's leading physicists were divided over whether the universe is a predictable machine or a fundamentally unresolved blur of probabilities. To settle the debate, researchers placed a detector at the slits to record which path the individual electron actually took. The moment the sensor was activated, the particle's behavior changed. It stopped acting like a wave and began passing through only one slit at a time, behaving exactly like a physical bullet. On the screen behind the slits, the wave pattern disappeared. It was replaced by two simple bands of particles, showing that the interference had ceased. Scientists attempted to rule out physical interference by reducing the detector's energy to near zero levels. Even when the sensor had no physical impact on the electron, the wave pattern still collapsed. The act of observation alone, the extraction of information, forces the sea of probability to collapse into a single, fixed state. In 2000, the delayed choice quantum eraser experiment took this concept even further by using pairs of entangled particles. One particle goes directly to a screen, while its entangled twin travels a longer path to a device that randomly records or erases its path. When sorted, erased information yielded a wave pattern, while kept information yielded a particle pattern. Because of the longer path, the machine's choice to keep or erase the data happens after the first particle has already struck the screen. This confirmed that a particle does not have a defined physical history until the information regarding its path is finalized. To this very day, the scientific community has no consensus on what these results mean for our understanding of matter. Various interpretations exist to explain the data. The Copenhagen model, which suggests reality only exists upon measurement, the many worlds theory, where every observation splits the universe, and the pilot wave theory, which proposes a real wave guiding the particles. While the meaning remains a subject of debate, the underlying mathematics are perfectly consistent and allow for incredibly precise predictions. Richard Feynman summarized this state of affairs by stating, "I think I can safely say that nobody understands quantum mechanics. We have now learned to calculate and utilize a set of universal laws that continue to challenge our internal logic." The hardware running this video is a direct application of these quantum rules. Semiconductors and flash memory rely on electrons behaving as waves of probability to move data through physical barriers, a process known as quantum tunneling. Both lasers and solar panels are engineered based upon the understanding that light possesses both wave and particle properties. Even our perception of time is synchronized globally through atomic clocks which operate by manipulating the quantum states of atoms. The double-slit experiment reveals that we do not live in a world of static objects. Instead, the very act of observation plays an active role in defining the physical state of the universe.